Good morning, students. I am Professor N.V.S.N. Sharma. Today we are going to see another topic in radar systems engineering, that is on navigational aids. Before we enter into the topic, we shall see a common example first. When we go on the roads, we will see several signboards indicating to the driver that there is a turn ahead or a bump or a school or a hospital, and accordingly the driver will be adjusting his speed to suit these conditions. Similarly, whenever there is going to be a junction, the driver will get the indication beforehand that if he takes a right turn, where is he going to, and if he takes a left turn, what will be the destination place, all these things. So accordingly the driver will adjust the speed and take the turn depending on the destination. Similarly, when we go on the train, we will see several signals like red, amber, green and so on for the driver to indicate what is the future course for him, and accordingly he will adjust the speed. Okay, on the roads we can place these signals or symbols and guide the driver to the destination safely. How about a ship or on a boat? So the signals are the aids provided for this purpose on the ship or on a boat are known as navigational aids. And the same logic or the same philosophy is extended to the case of aircrafts also, to guide the pilot to reach the destination safely within the time. So they are also known as navigational aids. So today we are going to discuss in detail different types of navigational aids used by the pilots for safe landing and for speed adjustments. Let us see from the basics of navigational aids. So today's class will be covering what is navigation, what are the conventional methods, what are the electronic methods for these things like ADF, Automatic Direction Finder, VOR, VHF, Omni Range, DME, Distance Measuring Equipment, ILS, Instrument Landing Systems, and so many more are there, but we will restrict ourselves to these 4 varieties, and then finally we are going to see what will be the future systems for the same purpose. Now let us see what is the meaning of this word navigation. Navis means ship, egere means to direct. So it's a device to direct the ship. Now let us see the standard case, that how do we get from Seattle to San Francisco by air. So once we take off from Seattle, you are in the air and you never know how to reach and how to change the direction and all these things. So here we need the help, that is to know where you are, where you want to go, about how much fuel and time it will take to get there. So this is what is supposed to be from the navigational aids. So first of all, how do I know where I am? So that is by pilotage, identification of present position and direction of flight by visual contact with terrain. Is it possible at all the times? It may not be so. So the procedure for air navigation has started with this. So aviation started in 1903. From 1919 onwards, people felt the need for navigational aids, so they started using bonfires and artificial lights in addition to landmarks and maps to help the pilots to find their ways. In this slide here, you are going to see the landing aids at different sites. There can be a flag which is waved by a person to indicate the proper path, or a landing field light is placed close to the runway to indicate the runway direction and location. So the history of air radio navigation, let us see. In 1920s started the use of radio navigational aids, or simply nav aids. In 47, the International Civil Aviation Organization, ICAO, was founded as a specialized aviation UN agency and NavAids internationally standardized. Several systems were then taken in use, and they are Ndb Non-Directional Beacon, which is meant to give the position information and the angle information, which we normally call as bearing, to the pilot. Then another one, DME, distance measuring equipment. As the name indicates, it gives the distance. Then VOR, VHF Omni Range. It's a misnomer in one sense that though we call it as a range, it doesn't give the range information. It gives the angle information, that is bearing. And finally, people have started using ILS, that is Instrument Landing Systems, particularly useful for landing purposes. So, let us try to understand what is the need for new navigational aids. It's by technology evolution. The availability of GPS and extended use of computers in flight management systems. Congestions in airspace. Need to increase the capacity by moving from today's route network to free flight navigation. Cost reductions. Need for more cost-effective use of aircraft by shorter stopovers and less fuel consumption. Lower navigation fees. Reduction of redundant navigational aids. Increased safety. Introduction of navigational aids for more areas and airports will increase safety and potential for fewer accidents. So, with these things, people started working out towards the present day, that is GPS systems. At this time, several electronic navigational aids are being used, which are shown in this slide here. Typically, one is a VOR and the other one is ILS. So, let's go into the navigational concepts. Here, we will start with a circle which has 360 degrees, and a degree has 60 minutes. 1 degree of latitude is the same distance anywhere on the earth. How many miles is 1 minute of latitude? The answer is 1 minute of latitude is equal to 1 nautical mile, or that comes to 2000 yards. So, nautical mile is larger than the normal mile which we count. Line of position is another definition which we all must be aware. A line that defines our position in one dimension. So, it need not be a straight line. Arc, circle, hyperbola or intersection of spheres can also be put into this. So, if you want it to be a straight line for this purpose, we need a second line to define a fix in 2 dimensions. So, need a third one to be sure about these points. So, what are the terms we use in this context? Navigational elements. If you want a point to be identified, we call that here as a fix. And bearing, that is the angle information, we get it from LOP. Range is also obtained from the LOP. Then if you have 2 angle informations, it will fix 1 point. 2 range informations if you have, it will also fix 1 point. If you have bearing and range of a location, it will also fix 1 point. But in the context of aviation, how they are mentioned is shown on the slide here. Then, how do we go to our destination without much of a wastage of fuel, time, etc.? So, first we plot a course. What's a course? It's a path of intended motion. Then, steer a heading is another word we use for this. What do I mean? What is that heading is? The direction the aircraft is pointed is known as the heading. Make a good track. What is that the track is? The aircraft's path over the ground. So, all these three terms are indicated by figures here. So a course is a straight line path, heading is the direction of the aircraft, and track is the path in which the aircraft is moving over the ground. So you can see how these things will be happening in the slide here. The nomenclature for certain things are to be known at this time. There is a true and magnetic courses, and they are given in 3 digits, that is 090 degrees. Relative bearings are given in degrees or clock position, that is 10 degrees left of the nose is one way people mention about this, or people may say it's 11 o'clock because it is left of the 12 o'clock position. And there is another one we call here, that is dead reckoning. Application of laws of physics will be used for this purpose as shown in the diagram here, and it is deduced reckoning actually, but in short people call it as dead reckoning. And there is a difference between heading and track. The heading represents the direction aeroplane is pointed. The track is the direction in which the aeroplane is moving, as shown in the diagram here. There is a difference between true north and magnetic north of the earth. The true north plus magnetic variation gives you the magnetic north. So here it is represented as a statement: east is least and west is best. That is, it is normally oriented slightly towards the west. So before we go to the conventional methods, let us see what are the devices we are going to use for this. A magnetic compass is the preliminary one. So here the magnetic compass indicates the north of magnetic pole of the earth, which is not exactly 90 degrees of north, but it is 82.7 degrees of north and 114.4 degrees of east. So there is a variation between the true north of the earth and the magnetic north of the earth, and this variation is shown in this diagram here, and it is going to vary slightly because of several reasons in the space. So those deviations are taken into account, and finally we conclude that the magnetic north wanders in an elliptic path each day and moves on the average more than 40 meters northward each day. So based on these details, we prepare a deviation table as shown in the slide here. And the magnetic compass which is used in the aircrafts is shown here in this diagram. And the compass will give rise to certainly some errors. Northerly turning errors. The result is a false northerly turn indication. Southerly turning errors. The result is a false southerly turning indication. And acceleration error. Like this, there are going to be certainly some errors coming up. And in addition to this, people have been using some other indicators like ADC, Air Data Computer, Air Speed Indicator, Vertical Speed Indicator, Mach Meter, Altimeter, like this. And here in this diagram, you can see all of them together as a front panel in this case, which work on pressure systems. So for this, we were using a pitot tube, and all these meters were aligned as airspeed indicator, vertical speed indicator, altimeter, and alternate static source is provided for this purpose. The pitot tube on the aircraft is shown in this diagram, and ASI, airspeed indicator, is given into this. The air is taken into the aircraft, and that will be given to the needle with a pressure tube like this. And it is likely to get into some errors because of the movements of the aircraft. and the wind velocity getting changed. Here, when we are talking of speed of the aircraft, we have certain definitions. IAS, indicated airspeed. CAS, calibrated airspeed. IAS, corrected for installation and position errors. EAS, equivalent airspeed. It is CAS corrected for compressibility error. TAS, true airspeed. EAS corrected for density. And the vertical speed indicator is shown in this diagram, and it indicates the rate of climb or rate of descent, which is measured in feet per minute or meters per second as the aircraft is descending towards the air runway. And a Mach meter is shown here, which is used to indicate the speed of the aircraft. It is indicated in terms of Mach 1 or Mach 2 and all, and the Mach is taken with reference to the velocity of sound as Mach 1. An altimeter is shown in this diagram with its cross section, and this altimeter is used to indicate the altitude or the height above the ground. And this height above the ground has again certain terminology. There is QFE and QNH. The regional or local air pressure at mean sea level is called QNH or altimeter setting, and the pressure which will calibrate the altimeter to show the height above the ground at a given airfield is called QFE of the field. An altimeter cannot be adjusted for variations in air temperature. Differences in temperature from the ISA model will therefore cause errors in indicated altitude. So QFE indicates aerodrome elevation pressure, and QNH indicates the QFE reduced to MSL according to ISA. So these different terms are indicated in this diagram to give clear picture of what we mean by QNH, that is mean sea level, above which you are going to get the height indication. But normally we are interested in QFE, above the ground of the runway, how much height the aircraft is of interest. And here there is a difference between the two words, height and altitude. The indicated height is QFE as datum, that is at the airport the baseline is drawn and above which the height of the aircraft is given as this indicated height. But if somebody is talking about indicated altitude, it means that he is talking about the QNH or the mean sea level as the datum. So true altitude is corrected for temperature and pressure. Then we have ADC, air data computer. Modern aircrafts use air data computers to calculate airspeed, rate of climb, altitude and Mach number. Two ADCs receive total and static pressure from independent pitot tubes and static ports, and the aircraft's flight data computer compares the information from both computers and checks one against the other. There is a gyro people have been using. A gyroscope is a device for measuring or maintaining the orientation. This orientation changes much less in response to a given external torque than it would without the large angular momentum associated with the gyroscope's high rate of spin. Since external torque is minimized by mounting the device in gimbals, its orientation remains nearly fixed regardless of any motion of the platform on which it is mounted. The stability increases if the rotor has great mass and speed. Thus, the gyros in aircraft instruments are constructed of heavy materials and designed to spin rapidly, even at the speed of 70,000 revolutions per minute. Attitude indicator. The purpose of the attitude indicator is to present the pilot with a continuous picture of the aircraft's attitude in relation to the surface of the earth. The figure to the right here shows the face of a typical attitude indicator. Heading indicator. Heading indicator shown in this figure, formerly known as directional gyro, uses the principle of gyroscopic rigidity to provide a stable heading reference. The pilot should remember that real precision caused by maneuvers and internal instrument errors, as well as apparent precision caused by aircraft movement and earth rotation, may cause the heading indicator to drift. Gyro drift. Because the earth rotates and because of small accumulated errors caused by friction and imperfect balancing of the gyro, the heading indicator will drift over time and must be reset from the compass periodically. The HI cannot sense north like a compass. The HI must be realigned with the compass about every 10 minutes. Height indicator is that HI is. The compass can be very difficult to read because it wobbles around. The HI is more stable and easier to read, but it must constantly be realigned. There is a flux gate. Some more expensive heading indicators are slaved to a sensor called flux gate. The flux gate continuously senses the Earth's magnetic field, and a servo mechanism constantly corrects the heading indicator. These slaved gyros reduce pilot workload by eliminating the need for manual realignment every 10 to 15 minutes. These are all the older methods, basically pneumatic systems. Now we have relative navigation systems based on electronic methods. So you can see here in this picture an airway structure between Ottawa and Toronto. There are so many intermediate points from which the pilot gets the indications between Toronto and Ottawa, and thereby he can see that the path is always the shortest and he will be able to reach within a short time by consuming very less fuel. What are the benefits of these relative navigation systems? These systems allow an aircraft to determine its position relative to a ground-based station, which we normally call here as facility, and most provide a bearing to or from the facility, that is the angle information. They are almost always used as intermediate points en route. Thus, the aircraft is usually flying directly toward or away from the facility. What are the examples of these things? These are non-directional beacon and automatic direction finder. Non-directional beacon will be placed on the ground, and automatic direction finders will be placed on the aircraft or on the port also. VOR is VHF Omni Range. It is a system which operates at very high frequencies. TACON, Tactical Air Navigation, and DME, Distance Measuring Equipment. Here we can have two types of approaches towards the runway. One is non-precision approach, wherein the pilot uses the data from Ndb and VOR for safe landing. And there is a precision approach also, that is using ILS, particularly the glide slope, and reach the runway very safe manner. Under poor visibility conditions, there is another type of approach we have known as ground controlled approach. The ground terminal people will send continuously the signals through a communication channel to the pilot to adjust his flight depending on the location of the runway and see that it is fully controlled from the ground station and there is a safe landing by that. So here we will see what is MDH and MDA. A minimum descent height or minimum descent altitude is the equivalent of descent altitude DA for non-precision approaches, and there are definitely some significant differences between these two. It is a level below which a pilot making such an approach must not allow his or her aircraft to descend unless the required visual reference to continue the approach has been established. That means the pilot can come down to a particular height above the ground. That is what we have, minimum descent height, below which he will not be permitted to come down. And unlike a DA, a missed approach need not be initiated once the aircraft has descended to MDH. The decision can be deferred to the missed approach point. That means if he is not able to come to that minimum descent height below the time, or if he has come down already ahead of the time, still he need not alert other people. There will be another chance for him to come to the actual height that is permissible. That is given by missed approach point MAP. So a pilot flying a non-precision approach may descend to the minimum descent altitude or maintain it until reaching the map, then initiate a missed approach if the required visual reference was not obtained. Now let us see the first of the navigational aids, that is Ndb Non-Directional Beacon. It is basically an omnidirectional antenna radiating the signals. It is placed or installed at different positions along the air routes, on the ground, and also at the airports. The purpose of this is just to give an indication where it is located. So the oldest navigation system is this non-directional beacon. The frequency of operation is between 200 to 500 kilohertz. The power it may be radiating is in the range of 20 watts to several kilowatts. The modulation it will be using is 1020 hertz tone plus Morse code identifier. That is about its location, where it is placed. The information is sent through a Morse code kept on a 1020 hertz signal, and the propagation of this signal is in the ground wave because it falls within the 500 kilohertz region. The Ndb is a ground based radio transmitter that emits a signal in every direction. What are the benefits? It's economical, easy to maintain, not line of sight communication it employs. So even under poor visibility it can send the signals, but the errors are due to interference from T-storms and bounces around coastlines. And there are three types basically. HH, that is high power transmitter, hence high range it can send the signals. So it is HH is more than 2000 watts of radiation which can send the signals up to 75 nautical miles. The H is 50 to 2000 watts radiation and the coverage will be up to 50 nautical miles. MH is less than 50 watts of radiation covering a range of 25 nautical miles, and a compass locator will be placed which will radiate less than 25 watts of power, and hence the range it can have is 15 nautical miles. Homing the Ndb. Flying the aircraft on any heading required to keep the needle pointed straight ahead of this Ndb. So works great without wind. Takes longer and not direct with wind. So if you are having an Ndb and if the path is straight away without wind, then it's going to be a rounded path when there is wind, as shown in the diagram. Tracking the Ndb. Tracking. Flying on a heading that maintains a constant or desired track to or from a station, and find heading or course that takes you to the station. Once if you are off by 10 degrees, double the deflection and turn towards the station is the indication to the pilot. Once deflection equals correction, you are back on the course. Turn 10 degrees towards the needle, repeat as necessary and become more precise with correction. Interpreting the signal from Ndb. You have to go for a parallel course, note the deflection, double it, so turn towards the needle is what you are supposed to do in the aircraft while understanding the Ndb signals. And this is to be corrected on a regular basis if there is wind, because of the changes that may appear. Other information transmitted by an NDB are Automatic Terminal Information Service ATIS and also Meteorological Information Broadcast or VOLMIT. The next one we are going to see is an Automatic Direction Finder. The purpose is to indicate in which direction you have to travel or in which direction the airport is, and the indicator in the cockpit for the pilot is as shown on the right side. And more closely you can have a look like this, ADF receiver for the pilot. The Automatic Direction Finder is to provide the pilot with a relative bearing from the aircraft to the NDB or to the airport. This is done using the directional property of a loop antenna. So the loop antenna is mounted so that it can rotate about the vertical axis, and its orientation is controlled by a servo motor. The antenna is rotated until the receiver detects the null, after which the null is tracked. The relative angle of the antenna is transmitted to the cockpit via a synchro system. So in the diagram here you can see the loop antenna and its radiation. A loop antenna gives a figure of 8 type of pattern as shown in the diagram. So one side will be a plus sign and the other side will be a minus sign for this. But for signals coming in the 0 direction or along 180 direction, you will get the same indication, and hence you will not be able to decide whether the airport is along 0 degrees or 180 degrees. So for this purpose we use another antenna which will have an omnidirectional pattern, that is a dipole. So mixing both the signals, you can now see that the total antenna pattern is going to be a Limacon pattern as shown in the diagram on the right. So the combination of the two antennas gives a Limacon pattern which has highest value at 0 degrees and very small value at 180 degrees. By this we can distinguish, if you receive a high output from the receiver, then it is going to be along 0 degrees the airport is. Otherwise, if it is going to be 0 degrees, then it is the airport is located along 180 degree location of the aircraft. But here there is a catch. As the signal is against a null, the sensitivity increases by increasing the gain of the loop antenna. This can be achieved by increasing the number of loops or increasing the loop area. A remarkable increase in gain can be obtained by tuning the loop to the frequency of the signal, realizing a resonance. At resonance, the output is sent through a capacitance which will have Q times more voltage than induced on the antenna. And to have a high Q 10 to 100, a square loop is used because it has maximum area for a given length, but a loop is more preferable. And the rotating loop antenna installation is large and causes excess drag and icing problems. It is also mechanical, which reduces its reliability. Thus, most modern ADF systems use a crossed loop system. A ferrite loop consists of a bar of ferrite material about which is wound many turns of fine wire is called Bellini-Tosi direction finder. The ferrite concentrates the RF magnetic field and allows a sensitive antenna to be constructed in a small space. Here in the picture you can see crossed loop ADF system, wherein the one set of loops will give k cos theta output, the other set will give k sin theta, where the k is the scale factor, and by combining these two we can get the exact information of this theta angle. So the block diagram of this crossed loop ADF is shown in this figure. The voltage induced in the coil proportional to the incident magnetic field will be as V cos theta or V sin theta. This is detected by phase detector, and the output is used to rotate the coil in a direction to reduce the phase difference by a reversible motor. The output of this two systems will be giving rise to an AM signal, and for the phase difference between 0 and pi, the output is positive, otherwise negative. This output and the reference signal are fed to a synchronous motor to control the motion. The ADF determines the bearing from the aircraft to the station. So needle always points to the station, indicates the relative bearing, and it is measured clockwise from the nose of the aircraft to the station. Card only indicates angle, has nothing to do with the direction aircraft is pointed. So the bearing indicator before the pilot is shown in this figure, and using relative bearing and magnetic heading, magnetic bearing can be found, and actual heading to fly to the station will be given by this equation. So from the Ndb, whatever is the indication we are getting, and by knowing the magnetic north, the direction in which the aircraft has to go further will be known to the pilot precisely with these informations. What are the types of ADFs? Fixed card, and it always shows the 0 degrees at the top. A movable card can show magnetic heading at the top, but it's a bad idea. And there is a RMI, radio magnetic indicator. It's slave to move with the aircraft. It's great to have such RMIs. So the types of ADFs are shown in this. The first one is the fixed card type, the second one is movable card type, and the third one is this RMI, which is the latest type in this. What about the characteristics of this ADF? The accuracy is 4.5 degrees. The availability is very high. 99.9% of the time it can be used or it can be operated. The integrity of this signal is the receiver monitors RF level and flag on indicator shows if level drops too low. The advantages of ADF are it's very cheap, reliable, and it's available almost all the time. But there are definitely some disadvantages. Only relative bearing is available. It's difficult to automate, susceptible to low frequency propagation effects like skip, refraction, skywave interference, etc. What are the recent developments in this? It is employed as an aid for homing. It fails to indicate only when there is lightning and also in the presence of lateral winds. To avoid this, the antenna is kept on fuselage to reduce this aerodynamic problem. Navigational aid, which is known as VOR, VHF, omnidirectional radio range, and these are assigned with the channels between 108 MHz to 117.95 MHz with 50 kHz spacing. A typical VOR system is shown in this picture. How does it operate? What are the things in this? Ground station oriented to magnetic north, transmitting directional information to aircraft but not the range. Hence the word range here is a misnomer. What are the benefits we are going to have with this? It's more accurate, precise flying you can get, reliable, not susceptible to interference, and it is voice capable. The errors are it's costly to maintain and the line of sight errors are likely to appear. So a VOR sends omnidirectional reference signal and directional signal from antenna rotating at 1800 RPM. A receiver uses phase information and navigation is possible in polar coordinates, that is rho and theta. What are the characteristics? The VHF, as mentioned already, operates in the range of 108 to almost 118 MHz. So it operates in the line of sight propagation system. So it can always take up one LOP at a time. So two receivers give two LOPs by which you can fix the point. So the two LOPs are obtained from VOR and another one from DME. And it is not sensitive to aircraft heading, and flight to or from a VOR or intercept a radial indicates the direction. So a VHF transmitter at airport radiates from an antenna of ADF, generates Limacon pattern. The pattern is rotated at 30 revolutions per second. Due to the rotation, the signal received in an aircraft flying along a particular direction will undergo a periodic variation at 30 Hz. The phase of the waveform depends on the bearing. To get reference for a phase, the transmitter is interrupted whenever the maximum of the pattern is due north. But this generates sidebands covering a wider RF band and may interfere with other equipment. So what are the types of VOR? We say high when it can radiate power more than 1000 watts. So 1000 to 14,000, 1500 watts, if we are radiating, it will be 40 nautical miles. And beyond that, up to 18,000, you can get 100 nautical miles of range. And like that, even 60,000 watts it can radiate, get 100 nautical miles of range. A low one is up to 40 nautical miles, and at the airport terminals we will have range up to 25 nautical miles. So the different types are shown in this diagram here: low, normal and high. What is the basic principle of this VOR? And the VOR receiver gives one LOP called a radial. So there are two parts in this. The ground based equipment is basically a rotating antenna which transmits a directional signal, and it rotates at 30 revolutions per second. The stationary antenna transmits reference pulse each time the rotating antenna passes through the magnetic north for phase reference. The aircraft set will measure the phase difference between the reference signal and the rotating signal, resulting in accurate track information, that is the radial information. What are the things in the receiver? The receiver will have VOR and ILS case, and the indicator will be course deviation indicator, radio magnetic indicator and horizontal situation indicator, and the antenna is usually on a vertical stabilizer. What is the operation? The desired frequency is tuned. Different airports will have different frequencies of allotment. As per that, the pilot will first set the desired frequency as per his chart. Then the OBS knob, that is Omni Bearing Selector, sets reference direction on the CDI or track the needle on an HSI. The station is identified. The CDI needle or track bar shows deviation from the selected course. So each VOR instrument incorporates a to or a from indicator. This is a to or from window on a CDI and an arrow on a HSI. The to or from indicator simply displays direction to the station. Signal warning flags are incorporated, so frequency monitoring is unnecessary. In an improved system, the reference phase is provided by amplitude modulation of omnidirectional transmission of 30 Hz reference signal. This modulation will have 30% depth, but 30 Hz reference phase is not distinguishable from 30 Hz modulation due to pattern rotation. So the output to the omnidirectional antenna is modulated by a signal of 9960 Hz that can be easily filtered out. This 9960 Hz is modulated by the 30 Hz reference signal. What about the receiver? The receiver is normally a superhet receiver The detected output is divided into two parts. One output is fed to a FM demodulator to recover the reference phase. This is compared with other output after limiting operation. Averaging the difference output will produce the signal proportional to the angle. What about the antenna polarization? The VHF band is selected to ensure low interference to other systems. Horizontal polarization is also chosen to reduce this further because all other systems operating in this frequency will be using vertical polarization. So, to get this horizontal polarization, we use magnetic dipoles, that is loops. So, a typical VOR antenna output will be shown to the pilot as shown in this diagram. How do we get the exact indication? Normally, we will have two receivers. The accuracy of the receivers may be checked against each other in the absence of the previous check facilities. Tune both the receivers to the same frequency, identify the directions on both, center both CDI needles, check needle sensitivity, and it must be within an accuracy of 4 degrees. Similarly, the VOR equipment also, first tune the VOR frequency, identify, confirm the position, center the CDI needle, check needle sensitivity, and it must be within 6 degrees. And the VHF signals associated with VORs are propagated through line of sight. Approximate range can be calculated by using the formula. The need for a ground-based station within line of sight range makes transoceanic VOR navigation impracticable. So, what are the limitations? The range is limited by line of sight. VORs are sensitive to the interference of terrain. The placement of VOR ground stations takes this account in most cases, but not always. Published airways are designed to avoid any unusable quadrants. However, care must be taken when navigating off airways. Published VOR radials are accurate within 3 degrees. Unpublished radials are not subjected to this standard. Any site-specific anomalies will be published in the CFS. The accuracy of VOR equipment is relative to distance from the ground station. A 1 dot CDI needle deflection at 1 nautical mile indicates a course deviation of 200 feet. A 1 dot CDI needle deflection at 30 nautical miles indicates a course deviation of 1 mile. If you attempt to fix your position using two VOR radials at an appreciable distance from the station and account for the allowable 4-degree receiver error, the accuracy is greatly undermined. Adding accurate distance information reduces this inaccuracy. That's the need for a DME, distance measuring equipment. So, what are the parts of this VOR system? So, we have in the receiver a course deviation indicator, and there is a special button for this to indicate whether we are going towards the station or away from the station. And on the left hand side you can see OBS, which indicates Omni Bearing Selector. So, from this you can see that when it is aligned properly in the course, then you can see that the indicator is perfectly vertical. Otherwise, there will be deviations from this towards the left or right, and accordingly the pilot will be moving the aircraft to make it central. So, the desired course is shown in this diagram as a red line, and the aircraft will be aligned with this, and the receiver for the VOR system is shown in this diagram here, which will have the set buttons already, and the frequency of operation is displayed. So, flying the VOR, initially tune, identify and twist, turn OBS to center needle and figure out the position. Note heading on top of the card. If flying from station, then to turn to that heading. If flying to station, put reciprocal heading on top and center, then turn to that heading. Give wind correction. So more correction is needed to get back on track if there is wind. So generally, when within 20 nautical miles, 20 to 30 degrees in direction of needle works. Once needle centers, turn backwards, original heading, but add wind correction of 5 degrees. Station passage. CDI will become very sensitive and then begin to oscillate. Flag will switch off from to, off and from. And switching radials. During station passage, turn OBS to new course to fly. Intercepting. If needle is alive, then turn towards it as if you were tracking it. If full deflection, first center the needle to find what radial you are on. Twist OBS back to desired course. Parallel that course, turn 30 to 60 in direction of the needle depending on the distance from the station. Once needle is alive, turn back in direction of desired course. Follow tracking procedures. What are the types of errors that are likely to come? Error increases with distance. Error increases with time. And reliability concerns are coming up, and there is a chance of human error in the entire procedure. Now, let us start the discussion on DME, distance measuring equipment. Before we go into the details of this, let us first understand what do we mean by a secondary radar. So far, in our radar system, we are assuming that the transmitter and the receiver are at the same place. The transmitter sends a signal and the target will be scattering that signal. The return signal from this target will be received and processed to get the range or angle information. So here the signal is traveling twice the distance, and hence we need high amount of power at the transmitter for proper operation of the receiver. But this is not the case with the secondary radars. There we will have a primary transmitter which will transmit a low power signal. At the target there will be another receiver which will receive this signal. With a certain amount of delay, it will transmit another signal. That will be received at the primary receiver point and processed to get the distance or angle information, etc. So a radar which will have two transmitters and two receivers will be known as a secondary radar. Distance measuring equipment is also a case of secondary radar. So here from the aircraft we will send a signal towards the ground station. The ground station antenna will receive these things, process it, and with a certain amount of delay it will transmit another signal. That will be received at the aircraft, and the total delay will be used to get the distance indication. So as in the figure shown here, you can see the distance is from the ground station and slant range is indicated, that is 20 nautical miles to 5 nautical miles variation you can get, though the aircraft is flying at the same altitude. From this slant range you can also estimate the exact height above the ground by using standard trigonometry. So a typical equipment placed at the ground is shown on the right side of this slide. DME provides information on the distance from the aircraft to the ground station. It is used to establish position along an airway and also to establish hold points. The DME operates in the range of 1025 MHz to 1150 MHz. In the aircraft, the ground system will be operating basically at 1025 to 1087 MHz, that is 63 MHz below the center frequency and 63 MHz above the center frequency, that is 1088 to 1150 MHz. So this gives 126 channels, and there will be two codings X and Y to double the capacity. The general principle is airborne transceiver transmits a pair of pulses spaced at 12 microseconds for mode X and 30 microseconds for mode Y. Ground transmitter receives these pulses, waits 50 microseconds and then transmits another pair of pulses back to the aircraft. Airborne transceiver measures the time between the transmission and reception, subtracts the 50 microseconds delay at the ground station, multiplies by the speed of light and divides by 2 to get the range information. This is very simple but gets more complicated when we want to service more than one aircraft. We need a method of distinguishing among the signals from up to 100 aircrafts. This is done essentially by generating a random set of pulses and correlating with the replies to determine the correct ones. The block diagram of an airborne transponder is shown in this figure here, wherein we have a crystal controlled synthesizer which can generate 126 spot frequencies around 45 megahertz. This is multiplied. The output power of the final amplifier is in the range of 50 watts to 1 kilowatt. There are two modes we can operate. One is a search mode and the other one is a track mode. The receiver of the interrogator can operate in both the modes. In the search mode, the demodulator pulse pairs due to the beacon reply signal are passed through a 20 microsecond gate delayed after a transmitter pulse by a variable amount increasing from 0 to 2400 microseconds. The transmitter waveform triggers the variable delay waveform, which in turn at the trailing edge triggers the 20 microsecond gating pulse. The variable delay causes the gating pulse to move on the time axis at a rate controlled by the rate of increase of the duration of the variable delay waveform. If this rate is synchronized with the rate of occurrence of the received pulse pairs converted to single pulses, all the pulses will pass through the gate. Otherwise, the number drops down drastically. Once a large number of pulses is indicated by the counter, system is switched to track mode. The pulse operation rate is then dropped to 25 pulses per second and automatic tracking is achieved. The accuracy is up to 150 meters. The transponder beacon uses similar equipment with more complexity, except that no ranging circuit is required. It operates at only one pair of frequencies. One's frequency pair is for reception, while the other one is for transmission. Different airports are given different pairs and the pilot knows about it a priori. The beacon transmits identification signals for a period of 3 seconds once every 37 seconds, when the normal chain of random noise pulses are suppressed. The received pulses are shown in this diagram. So if they cross the detection threshold, they will be identified as a pulse. If it is below, it will be identified as noise, and the time durations are also indicated. So this is given to the block diagram of a system as shown in the diagram below, and the input to output is done through a threshold detector like this. So what are the DME outputs? The output will be distance, and if you have a differentiator for this, it can be speed, and the distance by velocity gives you the time to the station also. The last two are valid only if the aircraft is going directly towards or away from the ground station. Normally, the DME measures slant range to the station. What we mean by slant range is direct distance from the aircraft to the DME station location. From this, you can also estimate the altitude and the range on the ground. So, the ground station simply receives a pulse pair, inserts the 50 microseconds delay and retransmits it. This is the basic operation of a DME ground station. To reduce the effects of reflections, it will not reply to another interrogation for about 60 microseconds, or what we call it as dead time. So to improve the operation, we normally go with a squitter. What is this squitter? The ground station transmits 2700 pulse pairs per second regardless of the number of aircrafts interrogating. The extra pulse pairs are called squitter. If there are not enough interrogations to make up 2700 pulse pairs, to improve the performance of ground station, we normally go with a facility called squitter.